Hi, this is an explanation for problem 98 from chapter 12. So this problem reads, your 300 milliliter cup of coffee is too hot to drink when served at 90 degrees Celsius. What is the mass of an ice cube taken from a negative 20 degrees Celsius freezer that will cool your coffee to a pleasant 60 degrees Celsius? To go about solving this problem, we need to find the temperatures of four different things really. So we're going to restate a pretty basic law that the transfer of heat is going to be a net zero movement. So we're going to get heat transferred from the coffee to the ice cube, but the overall transfer is going to be zero. So I broke this up into four different parts. We've got Q1, Q2, Q3, and Q coffee. Now Q1 through Q3 is the different phase changes of, sorry, I realized I wasn't even in the video. Let's try this. There we go. So Q1 is when we're heating the ice from negative 20 degrees Celsius to 0 degrees Celsius. Q2 is when we're melting the ice, so it's not really changing temperature, it's just undergoing a phase change from solid to liquid. And then Q3 is when we're heating the water that was the ice from 0 degrees Celsius to 60 degrees Celsius. And then Q coffee is just the change in temperature that the coffee undergoes. Now, to solve for these four Qs, we simply are going to use the constant values of ice, liquid water, and then heating water. We're also going to assume that coffee has pretty much the same properties as water because it's mostly water. So this isn't going to be 100% accurate with that assumption, but it'll be close enough for our purposes here. So to solve for Q1, we need to multiply the mass of the ice. I know all you animal lovers out there thought this said mice, but it's actually mass of the ice. Sorry to burst your bubble. And we're going to multiply that by the constant value, 2090 joules per kilogram Kelvin. And then we're going to multiply that by 20 degrees Celsius because we're raising the temperature from negative 20 to 0. We come up with a value that I just kind of erased with my hand on accident, but it's 4.18 times 10 to the 4th joules per Kelvin, and then that's still multiplied by the mass of the ice because that's what we're solving for, so we don't have that value yet. Q2 is going to be solved pretty similarly, but because we're not changing the temperature at all, we don't need to throw in a temperature. So it's just going to be the mass of the ice times the constant 3.33 times 10 to the 5th joules per kilogram. Q3 is going to be the mass of the ice times 4,190 joules per kilogram Kelvin times 60 degrees because we're again raising the temperature of water from 0 degrees to 60 degrees Celsius. And then Q coffee is going to be the mass, 0.3 kilograms, which we were given in the problem, times, again, the constant of water, 4,190 joules per kilogram Kelvin. And then we are decreasing the temperature of the coffee by 30 degrees, so we're going to then multiply it by negative 30 degrees Celsius. We'll come up with a value of negative 3.77 times 10 to the 4th joules. And then this one will not be multiplied by the mass of the ice. Okay, so now that we've solved for all of our Q values, we can go ahead and plug them into this original equation that we were talking about. Q1 plus Q2 plus Q3 plus Q coffee is going to equal 0. So we have our 4.18 times 10 to the 4th joules per kilogram plus 3.33 times 10 to the 5th joules per kilogram plus 2.51 times 10 to the 5th joules per kilogram. That's going to be multiplied by the mass of the ice, and then it's going to be minus 3.77 times 10 to the 4th joules, because again, remember we came out with a negative value. We're not actually subtracting that. It really is plus, but because it was a negative value, we're going to subtract that. That whole equation is going to be equal to 0. Now, when we algebraically combine the three Q1, Q2, and Q3 values, we come up with 6.26 times 10 to the 5th joules per kilogram. I then went ahead and added the 3.77 times 10 to the 4th the negative, sorry, I went ahead and added that to the other side in one step, and so we end up with the 6.26 times 10 to the 5th joules per kilogram times the mass of ice is equal to that Q coffee, the 3.77 times 10 to the 4th joules. And then if we algebraically solve now for M ice by dividing this Q value, this Q value right here by this Q value, we're going to be left with 6.0 times 10 to the negative 2nd kilograms, or if we go ahead and convert to grams, the ice cube will weigh 60 grams.